Good morning. Today we will discuss about the different source of noise in communication engineering. Subject is the principle of communication. So what is the noise? So noise is electrical term may be defined as any unwanted introduction of energy tending to interfere with the proper reception and reproduction of transmitted signal. Noise is mainly of concern in receiving systems where it set a lower limit on the size of signal that can be usefully received. Even when precautions are taken to eliminate noise from faulty connection or that arising from external source, it is found that certain fundamental sources of noise are present within electronics equipment that limit the receiver sensitivity. So, classification of noise. First, noise whose source are external to the receiver, and second is noise created within the receiver itself. So these are the classification in two types of noise source. Noise created outside the receiver and external noise can be further classified as first one is the atmospheric noise, second one is the extraterrestrial noise, and third one is the industrial noise. So what is the atmospheric noise? An atmospheric noise or static is generally caused by lightning discharges in thunderstorm and other natural electrical disturbances occur in the atmosphere. Since these processes are random in nature and it is spread over most of the radio frequency spectrum normally used for the broadcasting system, atmospheric noise consists of spurious radio signals with components distributed over a wide range of frequencies. It is propagated over the earth in the same way as ordinary radio waves of same frequency so that at any point on the ground static will be received from the thunderstorms, local and distant. Atmospheric noise become less at frequencies above 30 megahertz because of two factors. This first factor is higher frequency are limited to line of sight propagation or for example less than 80 kilometer or so. Second factor, nature of mechanism generating this noise is such that very little of it is created in very high frequency range and above. So cosmic noise and solar noise, these are the two noise. So what is the solar noise? Under normal condition, there is a constant noise radiation from sun simply because of its large body at very high temperature over 6000 degree centigrade on the surface. It therefore radiates over a very broad frequency spectrum, which is include frequency we use for communication. So due to constant changing nature of the sun, it undergoes cycle of peak activity from which electrical disturbance erupt, such as corona flares and sunspots. This additional noise produced from a limited portion of the sun may be greater or higher magnitude than noise received during period of quiet sun. So this is the solar noise. And cosmic noise. So what is the cosmic noise? So source of cosmic noise are distant stars as they have high temperatures. They radiate radio frequency noise in a similar manner as our sun, and their lack in nearness is nearly compensated by their significant number. The noise received is called black body noise and is distributed fairly uniformly over the entire sky. So this is the cosmic noise. And next one is the industrial noise. So in this type of noise, the noise range between 1 to 600 megahertz in urban, suburban, and other industrial area and is most prominent. Sources of such noise are automobiles and aircraft, ignition, electric motors, switching equipments, leakage from higher voltage lines, and a multitude of other heavy electrical machines. So these are the source of industrial noise. The noise is produced by the arc discharge present in all these operations. This noise is most intense industrial and densely populated areas. Next is the internal noise. So in internal noise, noise created by any of the active or passive devices found in receiver. Such noise is generally random, impossible to treat on individual voltage basis, but easy to observe and describe these noise because the noise is randomly distributed over the entire radio spectrum. Therefore, it is proportional to the bandwidth over which it is measured. So, internal noise can be further classified as first, that is the thermal noise, second one, sound noise, and third one is the low frequency or flicker noise. So, these are the parts of the internal noise. In thermal noise, the noise generated in resistance or resistive component is random and is referred to as thermal agitation, void, or Johnson noise. What is the cause of this noise? The free electron within a electrical conductor possesses kinetic energy as a result of heat exchange between the conductor and its surrounding. Due to this kinetic energy, the electrons are in motion. This motion is random through collision with imperfection in the structure of the conductor. This process occurs in all real conductors and gives rise to conductor resistance. As a result, the electron density throughout the conductor vary randomly giving rise to randomly vary voltage across the ends of conductors. So such voltage can be observed as a flicker on a very sensitive voltmeter. The average or mean noise voltage across the conductor is zero, but the root mean square value is finite and can be measured. The mean square value of the noise voltage is proportional to the resistance of the conductor, to its absolute temperature, to the frequency bandwidth of the device measuring the noise. The mean square voltage measure on the meter is found to be En square equal to 4kTBn. So this circuit diagram show the measurement of thermal noise, and the En root mean square noise voltage, where and R is the resistance of the conductor and T is the temperature in Kelvin and V is the noise voltage in Hertz. So K is the Boltzmann constant, equal to have the value of constant, that is the 1.38 into 10 to the power minus 23 joule per Kelvin, and the RMS noise voltage is given by En equal to under root 4 KRTBn. So this is the RMS noise voltage formula. Here note that thermal noise is not a free source of energy. To abstract the noise power, the resistance R is to be connected to a resistive load, and in thermal equilibrium the load will supply as much energy to as R it receives. In analogy with any electrical source, the available average power is defined as the maximum average power the source can deliver. Consider a generator of EMF, electromagnetic field, En volt and internal resistance R. So this is the a generator of EMF wave as shown in this circuit diagram. Assuming that RL is noiseless and receiving the maximum noise power generated by the R in that figure. Under these conditions of maximum power transfer to the load resistance must be equal to R, then in that case noise power equal to V square upon RL and also equal to V square upon R and equal to En upon 2 whole square upon R equal to En square upon 4R. So this is the Pn noise power formula, and also Pn equal to KTBn. So calculate the thermal noise power available from any resistor at room temperature 290 Kelvin for a bandwidth of 1 megahertz. Calculate also the corresponding noise voltage given that R equal to 50 ohm. So this is the example, and we can find out the noise energy with the help of these given parameters, and so put these parameters value of R, frequency and PL. So the En will be 0.895. So the thermal noise properties of a resistor are maybe represented to be equivalent voltage generator. Equivalent current generator is found using the Norton's theorem, using conductance G equal to 1 upon R. The RMS noise current is given by the IN square equal to 4G KTB, because G equal to 1 upon R, that is the conductance. Let's R series represent the total resistance of the series chain, where R series resistance equal to R1 plus R2 plus R3 and so on. Then the noise voltage of equivalent series resistance is En square equal to 4 RKTBN, where R is the series resistance and equal to R1 plus R2 plus R3, and put the R series value in this equation, and we have En square equal to 4 into R1 plus R2 plus R3 and so on KTBN, and also En square equal to En1 square plus En2 square plus En3 square and so on. So hence the noise voltage of the series chain is given by En equal to under root of En1 square plus En2 square plus En3 square and plus so on. Resistor in parallel. If we take the resistor in parallel, in that case, with resistor in parallel, it is best to work in terms of conductance. So let's conductance G parallel represent the parallel combination, where G conductance parallel equal to G1 plus G2 plus G3 and so on. So In square in the term of conductance G, 4G KTBN, and put here the value of G parallel conductance G1 plus G2 plus G3. So this In square will be equal to 4 into G1 plus G2 plus G3 and so on into KTBN. And also we have In square equal to In1 square plus In2 square plus In3 square and so on. Reactance. So reactance do not generate thermal noise. This follows from the fact that reactance cannot dissipate power. Consider an inductive or capacitive reactance connected in parallel with resistance R, as shown in this figure. In thermal equilibrium, equal amount of power must be exchanged, that is P equal to P2. But since the reactance cannot dissipate power, the power P2 must be 0 and hence P1 must also be 0. Next one is the shoot noise. So shoot noise is random fluctuation that accompanies any direct current crossing potential barrier. The effect occurs because the carriers, electrons and holes in semiconductors do not cross the barrier simultaneously, but rather with random distribution in the timing of each carrier, which gives rise to random component of current superimposed on the steady current. In the case of bipolar junction transistor BJT, the bias current crossing the forward bias emitter base junction carries the soot noise. When amplified, this noise sound as though a shower of lead soot were falling on a metal sheet. Hence, the name is soot noise. Although it is always present, soot noise is not normally observed during measurement of direct current because it is small and it does contribute the significant to the role to the noise. And the mean square noise component is proportional to the DC flowing, and for most devices the mean square soot noise is given by IN square equal to 2 IDC QE VN square amperes, where IDC is the direct current in amperes, QE is the magnitude of electronic charge, and VN is the equivalent noise bandwidth in the hertz. Now, next one is the flicker noise. What is the flicker noise? So this noise is observed below frequencies of few kilohertz, and it is spectral density increase with increase in frequency. So in spectral density increase with decrease the frequency. For this reason, it is sometimes referred to as 1 upon F noise. The cause of flicker noise are not well understood and is recognized by its frequency dependence. Flicker noise becomes significant at frequency lower than about 100 Hz. Flicker noise can be reduced. Now, significantly, by using wire-bound or metallic film resistor rather than the more common carbon composition type. In semiconductors, flicker noise arises from fluctuation in the carrier density, holes and electrons, which in turn give rise to fluctuation in the conductivity of the material. For example, the noise voltage will be developed whenever direct current flow through the semiconductor, and the mean square voltage will be proportional to the square of the direct current. In electronic devices, it shows up as a low frequency phenomena as the higher frequency overshadowed by white noise from other sources. Now we will discuss about the worst noise. So what is the worst noise? It consists of sudden step like transition between two or more discrete voltage or current levels as high as several hundred microvolts at random and unpredictable times. Each shift in offset voltage or current often lasts from several milliseconds to seconds and sound like popcorn popping its hook up to an audio speaker. So the most commonly invoked cause is the random trapping and release of charge carriers at thin film interface or at defect sites in bulk semiconductor crystal. In case where these charges have a significant impact on transistor performance, such as under an MOS metal oxide semiconductor gate or in bipolar base region. The manufacturing process such as heavily ion implantation. So a typical top or noise showing discrete levels of channels current modulation due to the trapping and release of a single carriers for three different conditions. We can see this in this waveform diagrams. Next, what is the spectral density? The spectral density is power distribution in frequency spectrum. It used to different type of noise, plot of light intensity, power as a function of frequency or wavelength. Thermal noise lies in category of power signal has spectral density. Bn is property of external receiving system and Vn assume flat. So from equation Pn equal to En square upon 4R equal to 4K RTBn upon 4R, and also we have Pn equal to KTBn. Since En square also equal to 4RKTBn, where En is the RMS noise voltage and R is the resistance of conductors and Bn is the noise bandwidth in hertz and K is the Boltzmann constant, which have the value of 1.38 into 10 to the power minus 23 joule per Kelvin. T is the conductor temperature in Kelvin. So available power spectral density in watt per hertz or joule is GAF equal to Pn upon Bn equal to Kt. Spectral density for mean square voltage is given by GBF equal to En square upon Vn equal to 4 RKTB V square per hertz. Since En square equal to 4 RKTBn, spectral densities are flat, that is independent of frequency as shown in this figure below. This is the relation between spectral density versus thermal noise spectral density. And so thermal noise is also called white noise because of analogy to white light that has flat spectrum, means signal contains equal power within a fixed bandwidth at any center frequency. When white noise is passed through a network, then spectral density is changed by shape of network frequency response. So the total noise power at output is sum of the noise distribution over complete frequency range, taking into account of frequency response shape. So consider a power spectral density response in figure below. In this figure, at frequency F1, the noise power for a small band with delta F about F1 is Pn1 equal to SP F1 delta F. Here delta F assume flat about F1. Delta Pn1 equal to spectral density in watts per hertz and bandwidth in hertz, or delta Pn1 equal to SP F1 dot delta F. So noise power is equal to area of shaded strip, that is in graph about F1, similar for F2, F3 and so on. That power is sum of all the small area, that is equal to total area under the curve. So area of curve gives total mean square voltage, and area of curve is the summation of GAF for F equal to 0 to F equal to infinite. So mean square voltage SP F1 into delta F equal to SP F1 delta F into B square. Area of curve gives total mean square voltage. So what is the equivalent noise bandwidth? So equivalent noise bandwidth, it is the frequency span of a noise power curve with amplitude equal to actual peak value and with same integrated area. If R is connected to input of LC filter as in figure A, this represents an input generators of mean square voltage spectral density 4R kT feeding a network of R and RLC circuit, that is in these two diagrams. Let transfer function of network includes RBHF. So spectral density for mean square voltage is equal to 4RKT HF square, where HF is ratio of output to input voltage for mean square voltage. So HF is the transfer function of the network. These are the frequency response between transfer function and frequency, and this is the LC filter and network. R is connected to the input LC filter in this circuit diagram, and input generator of mean square voltage spectral density have the 4RKT feeding network of R and LC filter. So the total mean square output voltage is given by Bn square equal to integration of 4KRT into HF square delta F, or the frequency of 0 to infinite. And we have also Bn square equal to 4RKTX area under HF square curve, or total mean square voltage at the output can be stated as Bn square equal to 4RKTBn. By above two equations gets equivalent noise bandwidth of network. So Bn equal to integration of HF whole square delta F equal to area under curve HF square for frequency of 0 to infinite. One example, consider in figure below input capacitance of the voltmeter used measure the noise voltage across a circuit diagram. So here RC network and its transfer function used in determining noise bandwidth. Transfer function of RC network HF modulus of HF equal to 1 upon 1 plus omega C R under root. So equivalence noise bandwidth of the RC network is Vn integration of HF modulus of HF into 2 DF equal to 1 upon 4 RC for the frequency 0 to infinite. So Vn square equal to 4k Tx1 upon 4 Rc equal to Kt upon C. So mean square voltage originate from R even though it's independent of R and inversely proportional to C even though C does not generate noise. So transfer function HF equal to modulus of Zc upon Zs, where Zs equal to R into 1 plus J by Q is impedance of the series tuned circuit, and Xc equal to 1 upon J omega C. That circuit is resonant at F0 frequency and noise restricted to bandwidth del F less than F0 about resonant frequency F0. So transfer function given by HF modulus equal to 1 upon omega naught CR equal to Q, and area under HF square curve of small bandwidth of delta F is Q square delta F. So mean square noise voltage is Bn square equal to 4 small r KTBn, and Q square R equal to Rd and frequency 0 to infinite, where Vn equal to 1 upon 4 RDC. Rd is the dynamic resistance of the tuned circuits. Noise bandwidth expressed as a function of 3 dB bandwidth of the circuit. So here assume that Q factor is constant and independent of frequency for end result, gives good indication of noise expected in practice but not true for range 0 to infinity. In radio receivers, noise is generated at antenna receiver inputs and output noise bandwidth is determined by the audio part of the receivers. Equivalent noise bandwidth equal to area of normalized frequency curve for low frequency section. Normalized means curve maximum value is unity. So the response curve show output in decibel relative to maximum as in next slide figure. These are some response curve. And equivalent noise bandwidth is area of curve for single sideband type, and noise bandwidth appears on both sides of the carriers and gets doubled. So these are the some response curve. First one is the amplifier frequency curve, and B is the curve of using linear scales, and C is the noise bandwidth of a double sideband receiver. So there are the different response curve. And what is the signal to noise ratio or SNR? In communication, it is the signal to noise ratio, absolute value of noise. It is defined as a power ratio S upon N equal to signal power to noise power equal to Bs square upon Bn square. Repeaters, amplifiers insert to make up of holes in for the loss in analog telephone cables. If power loss of a line section is L, Then repeaters amplifier power gain G is chosen, so Lg equal to 1. Long line divided into identical section. If input signal power equal to PS to first section as signal passes along the link power output at each repeater as a PS since Lg equal to 1. For each link what noise power are additive and the total noise at the output of nth link. So Pn equal to Pn1 plus Pn2 plus so on. In signal to ratio for a link, the m decibel is number of links expressed as a power ratio in decibel. So what is the noise factor? Noise factor is the ratio of available signal to noise ratio at the input to the available signal to noise ratio at the output. So consider a signal source at room temperature equal to 290 Kelvin providing an input to an amplifier. The available noise power from this would be Pni equal to K T naught Bn, where K is the Boltzmann constant and Bn is the noise bandwidth in Hertz. Here the available output signal to noise ratio will be less than that the input. So noise factor is defined as the available signal to noise power ratio at the input divided by available signal to noise power ratio at the output. So F equal to P n naught upon Gk naught Bn. It follows from this that the available output noise power is given by P naught P n naught equal to F G K T naught Bn. So the available output power depend on the actual input power delivered to the amplifier. So noise factor is a measured quantity and will be specified for a given amplifier or network. It is usually specified in decibel when it is referred to as the noise figure. So thus noise figure equal to F in decibel 10 log of F. This is the example for calculation of the signal to noise ratio. There are given some parameters, and with the help of these parameters, we find out the signal to noise ratio. Next one is the noise temperature. The concept of noise temperature is based on available noise power equation Pn equal to KTBn. Here the subscript has been included to indicate the noise temperature is associated only with available noise power. In general, TB will not be same as the physical temperature of the noise source. So an example antenna pointed at deep space will pick up a small amount of cosmic noise. The equivalent noise temperature of antenna that represent this noise power may be a few tens of kelvins. Well below at the sun, the received noise power increase enormously and the corresponding equivalent noise temperature is well above the ambient temperature. So when the concept of applied to an amplifier, it related to equivalent noise of the amplifier referred to the input. If the amplifier noise referred to the input is denoted by PNA, the equivalent noise temperature of amplifier referred to the input is PE equal to PNA upon KBN. So PNA equal to f minus 1 into kt naught Dn. So we get equivalent noise temperature of the amplifier in term of noise figure Te equal to f minus 1 upon Ta. This show the proportionality between Te and F. In practice, it is found that noise temperature is the better measure for low noise device such as low noise amplifier used in satellite receiving system with noise factor is better measures of main receiving systems. These are the some reference books which covers this topics. The first is analog communication by Bhatt and Rao. Second is digital communication by the T.L. Singer. And there are some also multi-choice questions here for clear the concept of these topics. Thank you very much.